Welcome to the lecture. Today we will switch to a new topic, which is also the last part of this course. We will talk about cluster algebra arising from Riemann surface. We actually have encountered already a special example, a special case of triangulation of polygons. So if we have a polygon, then we can consider the triangulation. To each triangle, we will associate a quiver by joining the midpoint of the triangles in, say, a counterclockwise way. So this quiver will give you a cluster algebra structure of geometric type. And remember, the interior vertex, the interior midpoint, will be the mutable vertex, while the vertex on the side of the polygon will be the frozen vertex. We can also talk about mutation, which corresponds to flipping of the diagonal. Then we know that the quiver corresponds to the flipped polygon, will be related to the other one by a mutation, a quiver mutation. So everything is compatible in the cluster algebra side. Today we will talk about a more general setup, which is the triangulation on general Riemann surface. And we will look at the combinatorial aspect of it, how we can associate a quiver and then a cluster algebra from the surface, and some problems arising from it. For example, when there's a self-folded triangles, then we cannot really flip the diagonals. And we will try to resolve this by introducing an extended version of the triangulation known as attacking. So today we will talk about only the combinatorial aspect, and in the next class we will give it a geometric meaning in terms of hyperbolic geometry. So it turns out that these triangulations naturally are realized by geodesics, and the hyperbolic distance of these geodesics will give you a coordinate system known as the lambda length on the type-Euler space, which describe the collection of hyperbolic structures on your Riemann surface. And this notion will lead to a generalization known as the higher type-Euler theory, which will play a very important role and it's very popular research area initiated by Fogg and Goncharov. And we will discuss this in the class next week. All right, so let's start by defining the surface that we are of interest. So in this lecture, we will be considering bordered surface with marked points. This is a pair S and M, where S is just the Riemann surface, which will be connected, oriented to real dimensional Riemann surface, and possibly with a boundary. M will be the marked points, which is just a finite non-empty finite set. So the marked point can lie on the boundary or lie in the interior of the surface. If they are in the interior, then we call them punctures. And we also require that each connected boundary components to have at least one marked point. Oops. So in the very special case, we will say that a disk with n mark point on the boundary will be known as the n-gon. So it will look something like this. So the pentagon will be realized this way. And in terms of Riemann surface, we will consider this as, say, a sphere with one boundary component. So this will be a sphere having a big hole and 5 mark points. So these two are the same picture. So this will be a hole, so there's nothing in here. So you cut out the sphere with one boundary component. So maybe a more elaborate example. So say this picture, this is a torus. So it has two punctures. It has one boundary component. And altogether there are 5 mark points. 3 of them lie on the boundary component. And in this case, we treat this as a torus. So the genus of this surface is 1. So it is a torus where you cut out a hole and you put 3 points on the boundary and 2 points in the interior. All right, so then we will define the notion of triangulation. So triangulations will be a curve joining different mark points on your surface. So we'll define this as an arc. So an arc in your bordered surface will be a curve up to isotropy. So you can move around the curve a little bit before crossing each other, such that the endpoints should start and end on the mark points. And it should not self-intersect. Except maybe at the endpoint. So you cannot have such thing, but you're allowed to have the same endpoints. So this is okay. And gamma should be disjoint from M outside the endpoint. So it can only join different mark points, but the interior of this curve should not cross any mark point anymore. And the boundary also. And finally, this is a technical condition where we allow the curve to cut out a 1 gon or 2 gon with no punctures. So 1 gon means a loop with just one mark point. So this is the 1 gon. So and this is interior here. So let me just think. So this should be a one gon, and you don't want it, and a two gon with no punctures. So how can you cut out a two gon? Well, for example, you have a boundary, and your curve start and end at the boundary. But if you draw such a curve like this, then this will be a two gon with no punctures, and you do not allow this situation. So we say that two arcs are compatible if they do not intersect in the interior of your surface. And we will denote by A0 to be the set of all arcs. Again, up to isotropy. So then naturally the the definition of triangulation will be a maximal collection of all pairwise compatible arcs so that each arc do not intersect with the other. So we call this the ideal triangulation. So this will be the maximal collection of pairwise compatible arcs. And the arcs together with the boundary of the surface will cut the surface into ideal triangulations. Ideal triangles. So the word ideal really comes from hyperbolic geometry. So in the next class, we'll realize these triangles where all these arcs will be given by geodesics of the hyperbolic structure of the hyperbolic metric. And ideal triangles really just means that the free sides of your triangle will be given by geodesics. So as a remark here, we note that we will allow self-folded triangles. So this will be triangle of the following form. So this is a triangle, right? Because you have one edge, and then the second edge, and then the third edge back. So this is like a triangle, but you stick together two sides of the triangles, two of its sides. So this triangle is okay. And one can easily count that each ideal triangulation will consist of n arcs, where n is given by 6g plus 3b plus 3p plus c minus 6. So G will be the genus in the sense we discussed before, and B will be the number of boundary components. P stands for punctures, and C will be the mark points on the boundary. So those mark points that are not punctures. So because we want to work with triangulation, then definitely we want to ignore all those special examples where there are not enough triangles. So in our setup, let's say remark, in our setup, S should have at least one arc. Otherwise, you cannot do anything. So S cannot be the following list in our consideration. So it is a sphere with 0, 1, or 2 punctures, a 1 gon with 0 or 1 puncture, and a 2 gon or 3 gon with no punctures. So 1 gon with no puncture looks like this, and with a puncture looks like this. So we do not allow that. And 2 gon with no punctures will be this, and 3 gon with no puncture is just the triangle. And we ignore the triangle because although it is a triangle, all 3 sides are the boundary of your surface, so there are no interior arcs. So n is 0 in this case. Oh yeah, arcs. So arcs always means the curve in the interior of the surface. So in the special case, we will also ignore it because they are just too special. So in the special case for n equals 3, so that your surface has a single triangle in the interior, then either the surface with genus 0 and 3 mark points, so it is the sphere with 3 mark points, and a torus with 1 mark point. So this all consists of 3 edges and 2 triangles. So the 3 edges of your surface will be shared by 2 triangles in 2 different ways, and this kind of causing some troubles in the consideration, so we will ignore this case as well. So for a sphere, then you can see that this is a triangle, but the remaining part of the sphere is really another triangle because it also has 3 edges on the side. And similarly for the torus. So for torus, if you realize it as a square where we identify the sides, and let's say this is the puncture, the mark point, then again this will be 2 triangles, but the 2 triangles will share all 3 sides. And we do not want to have these examples. All right, so now we have the triangulation. We can flip the triangles just like before. So simply, if you have 2 triangles in this configuration, then you flip the diagonal. And in the special case, when you have self-folded situation, more precisely this type, then you can flip this edge. Then you're really interchanging the vertex. So the triangle, instead of these 2, now you are joining this and this. So just think of cutting this edge and treat it as just the usual triangulation, and you flip, and then you glue it back. So these are really the 2 possible flip of triangles. And now you can see the situation I mentioned earlier is that you cannot really flip this edge because it has nowhere to go. Right. So we will try to resolve this situation later. But now let's talk about the arc complex. So this is a simplicial complex. So the idea we have already covered several times before in the case of triangulation of polygons. So each vertex will correspond to the arc, and each simplex will be compatible arcs. And then of course the maximal simplex will be the maximal compatible arcs. And then this corresponds to ideal triangulations. And we can also talk about the dual graph. And we denote this by E. So for the dual graph, then the vertex will be triangulations, while the edge will correspond to flip of the triangles. So just look at a simple example. How can... Right, so this is an example for a triangle with one puncture. So this will be the arc complex, and this will be the dual graph. And then you can see that each vertex of your arc complex will correspond to a arc, right? So this is an arc, this is an arc, this is an arc, for example. So each vertex of your arc complex corresponds to an arc, and then for a simplex, a maximal simplex, so in this case a triangle, will correspond to a triangulation involving, say, this arc, and this arc. And you can see that this triangulation is precisely the one here. So this is the dual graph. So the maximal simplex will correspond to vertex on the dual graph, while for the edge of a graph of the dual graph will corresponding to a flip of the triangles. And a flip of a triangle really means crossing through the other maximal simplex. So you are really trading one arc with the other arc. So one thing to notice is that this arc complex has a boundary, right? So this is the boundary of your arc complex. There's nothing outside this picture. And these are all the simplex of your arc complex. And on the other hand, the dual graph is not free regular, because there are some there are some cases where you cannot really flip the arc. So that we mentioned already, you cannot flip such an arc inside a self-folded triangles. So it is not free regular, you cannot go in other direction. But for a cluster algebra, we really want to be able to mutate at every mutable vertex. So we want our exchange graph to be free regular. So this is why we will like to extend the definition of triangulations so that we can cover more special case, more general case, and allow the corresponding dual graph to be free regular and then compare it with the cluster algebra exchange graph. But in any case, let's first study several properties of this complex. So the first proposition is that the arc complex is contractible unless it is a polygon with no punctures. So if it is a polygon with no punctures, then it will be isomorphic to a n-sphere. Our dual graph will always be connected. And this really is just saying that you can obtain any triangulation from another by flipping. Right? Because the edge really just means a flip. So if it is connected, then you can flip from one triangle to another triangulation. And furthermore, the fundamental group of your dual graph will be generated by the 4 or 5 cycles. Yeah, so when we talk about E0, the dual graph, we only talk about graph. So we only care about the 0 simplex and the 1 simplex. So these are like all holes. There's nothing here. And then the fundamental group, really just saying that all these holes are either pentagon or a square. But just like the Grassmannian case that we discussed before, there's always a canonical good choice of such a triangulation. So the claim is that for every border surface, you can always find a triangulations with no self for the triangle. Which means that if you start with this triangulation, you can mutate in, or you can flip in all directions. So you can flip every internal edge of this triangles. So in this example, then this triangle will be the good one because it has no self for the triangle. But of course, the highlighted one is also good. All right, so this is the triangles, and now we would like to associate to it a quiver so that we can define cluster algebra of geometric type. So let me just redraw again. So for a triangle, we will associate a quiver by joining the midpoint of the triangle. Then a flip will correspond to quiver mutations. Right, when you it's the same as mutating in this vertex. So flip equals quiver mutations. So we just associate to each triangle such a quiver, then we'll get an extended exchange matrix, and we will obtain cluster algebra of geometric type, starting from this extended exchange matrix. And let's say we start from the initial one, so the one that has no self-folded triangles. So every triangle is nice of this form, and you know how to associate to it a quiver. So in this case, the n means the number of arc of your triangulation, the number of mutable vertices. So this will be labeled by arcs, and then the remaining variables will be the frozen and labeled by the size of S. So the size of S means that the connected components of your boundary subtracting, removing the mark points. So if you have a boundary and mark points, then the connected components will be these three. So free components. Right, so we start from a triangulation where every triangle is nice, and we can associate to it a quiver and obtain a extended exchange matrix and then a cluster algebra of geometric type. So what happens if we mutate or if we flip the triangle so that we obtain a self-folded one? Well, then naturally the quiver corresponding to this self-folded triangulation should be the same as the quiver obtained by mutating the corresponding vertex. Right. So it turns out that all the cases can be summarized in 3 puzzle pieces. So it turns out that all possible triangulations can be composed of just the standard triangle and a piece with one self-folded triangle and a piece with 2 self-folded triangles. And the quiver corresponding to this self-folded case is listed here in terms of a matrix, but you can also just write down the draw the quiver. So it will look something like this. And this is definitely obtained from mutating at 3 of the standard quiver, right? If you mutate at 3, then this is really just this. And the corresponding quiver will be of this form. Because the arrow from 3 to 4 and 4 to 3 will cancel. So you are only left with this. Or maybe I flipped the orientation. Yeah, anyway. So similarly, this picture will correspond to quiver of the type. So this quiver is this. Oh yeah, the convention here is kind of flipped. So it has 1, 2, but it is clockwise instead of counterclockwise. Maybe I should flip change everything in terms of minus. Yeah, because I used to have the version where you use the counterclockwise version. Anyway, so yeah, so just up to the sign. Every triangulations can be composed of a standard triangle, is one self-folded or two self-folded pieces. And this one can be found from the standard triangulation by flipping at 1 and 4 and 2. Right. So I think it should correspond to such a picture. Ah, no, not this picture. It corresponds to this picture, which everything is actually good triangles. They did not self-fold it. So as a corollary of such an association, then it is clear that our previous arc complex will be a subcomplex of the cluster complex of your algebra. And similarly, the dual graph will be a subgraph of the exchange graph of A. So this just follows from definition, right? Because we are associating triangulations with an extended exchange matrix, which is like a seed of the cluster algebra. And whenever you mutate, it corresponds to flip. So this will be a subgraph. But because for the cluster algebra case, you can exchange more in a situation where we cannot really flip. So this picture will be smaller. But then naturally, we now want to extend the definition of the triangulations so that we can allow flipping of such a self-folded triangles so that the combinatorics of triangulation will match the cluster complex. But before we go on, let's look at several examples of cluster algebra arising this way. So remember, all we need is to consider the setup where we start from a good triangulation with no self-folded triangle. So first very trivial example is a foregone with no puncture. Then in this case, we really have one triangulation. We really have two, I should say, one arc and two possible triangulations. And this corresponds to just a cluster algebra with one mutable vertex and four frozen variables. So remember, when we talk about the type of a cluster algebra, we only care about the mutable part. So in this case, this is a type A1 cluster algebra. And for five-gon, we encountered this right from back in the first lecture. So this will be a type A2 cluster algebra. Because the mutable part, the quiver correspond to mutable part is just this rank 2 quiver. How about a two-gon with one puncture? So a two-gon with one puncture looks like this. And if you look at the mutable part, So it will be the quiver joining these two midpoint. But as I mentioned, if you draw the arrows, then they actually cancel. So the quiver is really just two dots without any arrows. So this will correspond to cluster algebra of type A1 cross A1. And finally, for freegon with p equals 1, so this is the picture we have previously. So if we use this standard case, then we can draw the quiver. And say if we mutate once, we will get such quiver, which means that the cluster type corresponds to A3. So a torus with p equals 1. So let's just draw a torus. So this is the special case that I mentioned, but we can still assign quiver and still talk about the cluster type. So it will be of this form. So if we draw the quiver like this, but remember that the sides are identified. So if you just draw it out, you see that it really is of this type. And this we already know is the Markov quiver. So these are very small rank example. So let's look at some family. So we have already seen previously that type AN cluster algebra arises from the triangulation of n plus freegon with no punctures. And type Dn will be coming from n-gon with one puncture. So we have already shown this, but let's also look at it again. So this comes from the slick diagrams. So this will be type AN, and this will be type DN. Right, so if you draw the quiver, then you see that the mutable part will be a straight line. So it is the type AN. So you don't care about the arrows which points to the frozen side. So the full quiver will look something like this. But all these green arrows will be joining some frozen vertex, and we don't care about that. We only care about the interior. So in this case, you have 5 interior vertex. So this is type A5. Similarly, for type D, will correspond to n-gon with one puncture here. So again, if you draw the mutable part, so you see that this will be a thinking quiver of type D. So you may notice that this is a self-folded case, so these two arrows will cancel, so you don't have this part here. Yeah, anyway. So there are more examples where it is not of a finite thinking type. So we have the following lemma. So assume we have an n cycle, Then it turns out that the mutation equivalent class depends only on how many arrows pointing in the counterclockwise or anti-counterclockwise, clockwise or counterclockwise direction. And this is an unordered pair. So if you have an n cycle, you just count how many arrows are pointing in one direction, how many arrows are pointing in the other direction, and then the mutation equivalent class will only depend on these two numbers. And we will define the type of such a cycle to be a tilde of an1 and an2. So a tilde naturally corresponds to the affine the affine D type of A, which is a cyclic Quiffer. And we also note that previously we have shown that if all the arrows are pointing in the same direction, so either all pointing clockwise or all pointing counterclockwise, then we know that we can do a mutation and turn this into a type Dn Quiffer. So another affine type is the affine Dn. So it will be of this form, the endpoint. I mean n vertex. Now we can associate, we can realize this two type with the following surface. So for type A, this can be realized as an annulus with no puncture and n1 or n2 mark point on the boundary. So an annulus where you will have two boundary, this boundary and this boundary. So an annulus has two boundary, and then on each boundary you have n1 mark points and n2 mark points, and then you draw out the corresponding triangulations. Then you can see easily that this will give you the necessary Quiffer. I hope I'm drawing correctly. Yeah. So you can see that here you have some arrows pointing in one direction and other arrow pointing in the other direction, and it combines to this cyclic Quiffer. And similarly for the affine D type, will correspond to n-2 gon with two punctures, as you can see in this example. So you can see that this is a affine thinking type Quiffer. All right, so that's kind of the main realization of cluster algebra of finite mutation types in terms of some special choice of surface. So the next goal will be to extend our triangulation so that we can resolve the case that we cannot do a mutation or we cannot do a flip of the self-ordered triangles. So this combinatorial object will be known as the tagged arcs. So the tag arc will be an arc with a tagging. So a tagging can have two types. Either there's no tagging, so I put the empty set symbol here, or sometimes it's called plain. So this will be the standard. I mean, it's just do nothing, or you let's say put a bow tie. So the tagging should be put on each end of the arc, such that there are several conditions. The endpoints on the boundary should be tag plane, so there should not be any tagging in the endpoints lying on the boundary. Both ends of a loop is tagged the same way. So if you have a loop, then either you have no tag or you have the bow tie tag on both ends. And finally, the arc does not cut out one gon and one puncture. So this is an extra condition of the arcs. So we do not allow such a situation to happen. Oh, actually, we do not allow this already previously. Really? No, we allow this. Yeah, so this is an extra condition. We do not allow the arc to cut out a one gon with a puncture inside. Then we just extend our set and consider the set of all tag arcs. So naturally, there is a map from the tag version to the untagged version. So yeah, so this is really called the untagged version. You simply forget the tagging. So there's a natural map. But we can also introduce a map in the other direction called the replacement. So it's divided by tau from the untagged version to the tagged version. So this is defined as follows. So if the arc does not cut out one gon with one puncture, then we just put it as the original one without tag. Yeah, so in the previous triangulations, we allow the arc to cut out one gon with one puncture. But for the tagged arc, we do not allow that. So what happens then? So if your original arc cuts out a one gon with one puncture, and let's say we label this by A and B, then we will replace this with a tag arc, where the tagging is on the puncture side. So basically what we are doing is to replace all the triangulations with one puncture and one gon with one puncture into some tagged version. And this will allow us to do flipping of this edge, because now it will look something like this, and we can introduce the tag flipping to resolve the set for the triangles. But first, let's again introduce the tag arc complex, which means the set of compatible arcs. So we say that two arcs two tag arcs are compatible. If, first of all, the corresponding untagged version is compatible. And if the two untagged versions are not the same, but they share an endpoint, then they should be tagged the same way at that endpoint. So something like this. So if you have two arcs, then they should be tagged the same way at the common endpoint. And if the untagged version is the same, then they are tagged the same way in at least one endpoint. So in this example, something like this. So in this picture, the two arcs will have the same untagged version because everything is up to isotropy. So you're just talking about two arcs drawing the same 2 points. And so here it says that you should have the tagging the same in at least one endpoint. So either this or maybe tag is okay. But you cannot have situation like this. So we just define the tag arc complex as before. So we'll denote this by the bow tie and then the dual graph. And the maximal simplex will be called the tag triangulation. And a very simple observation is that if your surface has no puncture, then automatically the tag complex will be the same as the untagged version. Because I mean, if you have no punctures, then there's no such replacement at all. You don't have everything like this. So now we can extend the previous picture to a higher rank. So in this picture, for example, previously we have a two-gon with one puncture, and after we flip, we have this edge here that we cannot do any more flipping. But now after you do the replacement, you're replacing this outside edge. You're replacing this outside edge with this tag arc. And then it turns out that there's a new triangulation that is compatible. or there's a new edge that's compatible with the edge, with the inner edge. So here we see that this will correspond to what's called the tag flipping. Right. Yeah, so this basically says that the arc is compatible with each other, so you can construct a new triangulation here. And another example extending the previous picture. Too big, too big. So this is our previous picture. And now you can see that previously we are only bounded by this collection. But now you can extend to a new triangulations. I mean a new tag arc. So this arc will be compatible with this, and with this. And so you extend your previous arc complex to a complete version. And if you recall the cluster complex for the triangulation of hexagon, you will see that they are actually the same picture. So I mean here, this is the E of the hexagon, and this is the delta tag of one puncture triangle. But the dotted lines here will be the dual simplex. So if you look at the dotted line, you'll see pentagons. You see something like pentagons. You can see square, and so on. And you can compare that these two are the same. And this is actually not surprising because we have already seen that this provides us a cluster algebra of type A3, and this is also of type A3. So these two exchange graphs are really just the isosahedron of type A3. So the main difference is that they have different number of frozen variables. For the hexagon, you have 6 sides, so there are 6 frozen variables, while for the triangle, you only have 3 frozen variables. But otherwise, the exchange graph is the same. So this, for now, is like a observation. So we really need to prove that after we introduce such a tag triangulation, the corresponding cluster complex actually is the same as the cluster complex of your cluster algebra defined from this initial triangulation. And the point really is just to compare the quiver behind the mutation. So we really need to understand the tag flipping because we have a quiver in your initial and then you mutate to some point where you have a self-ordered triangle, but we know how to do that. We are just doing quiver mutations. Then you want to mutate in the forbidden direction and you get some other matrix, and then this matrix should naturally corresponds to the matrix of the tagged version. And then we just need to check that the tag flipping is compatible with such a quiver mutation by defining the tag flipping rules explicitly. So I have some free space here, so let me write first the proposition. So this is some small observation that if your surface is not closed, so it has a boundary, and with exactly one puncture, then the dual graph and the arc complex are connected. But otherwise, the graphs and arc complex will have two isomorphic components. Why? Well, one will have the tagging at the puncture, and one will have no tagging. One will have no tagging, one will have tagging. And these two will never reach each other. So your cluster complex will consist of two pieces. At all the punctures. All right, so the statement that I mentioned just now is that the cluster algebra corresponds to the marked surface, and if the surface is not a closed surface with one puncture, then the cluster complex will be the same as the tagged arc complex. And the exchange graph, the isosahedron, will be the same as the exchange graph of the border surface. And otherwise, we know that the tag arc complex and the exchange graph has two isomorphic components, then the data will be corresponds to a component of either component of the tagged complex. So as I mentioned, the proof of this comparison really is to study or define the tag flipping through the use of Griffin mutation. So let's define what exactly is the tag flipping. So let's first define several notations. So the undone version of a triangulation so this is just an ordinary triangulation where if all the arcs from the function has a tagging, then you just remove the tag. And otherwise, you replace gamma with a loop to undone the replacement map tau. So just as an example, again, if you have a puncture and you have tagged the same way everywhere, then you just use the original triangulation. And if you have a puncture where they are tagged differently, then you just replace it with the inverse of tau. So remember, tau maps this picture to that picture. So you just reverse it, and you can always do that. So now what are the tag flipping? So tag flipping will have two types. So the first type is called the diagon flip. So diagon means two gone. And this is exactly the picture that we draw before. So you flip the one without tag and add a tag like this. And the second type is the quadrilateral flip. So this is the standard flips in the undone version. Right. So the picture here, you want to flip from here to here. What you do is first you undone your quiver. So you're replacing the tag arc with a loop around the puncture. And now you can do the flip. So we are interested in doing the flip of this arc. So after you do the flip and then you go back to the tag version. Yeah, so basically you undone your picture and then you do the flip and then you do it again. Yeah, I mean, and then you replace it back with the tag version. Now the theorem follows from the fact that if we define the exchange matrix of a tag triangulation as the exchange matrix of the undone version, then it satisfies the same mutation rule with the tag flipping. So as an example, this is the cluster complex, the arc complex for the tag version, and you can see that the diagon flip, for example, this is the diagon flip, this is also the diagon flip, and the diagon flip here is flipping vertex free, and you see that it is the same as just mutating at vertex free, and that this vertex and this vertex are really the undone version, and they share the same exchange matrix. Is it up to a permutation? No, they should share the same. Yeah, because the index is switched. You can see it's 1 3 3 1 here. Yeah, so so they're not really the undone version. I mean the undone version will be 4 3 1 2. The index switch. So yeah, the arrow switch. But then this actually associate to this grapher. So now with the corollary is that cluster algebra from surface is of finite mutation type. And this simply is because all the adjacent C matrix. So the matrix corresponds to quiver, which, as we mentioned, is only built up from the three puzzle pieces. So in particular, they can only take value 0, 1, or 2. So this means that you can only have finitely many different triangulation of a surface. All right, so this kind of concludes the discussion of the triangulation. So one particular application is the Denominator Theorem. So if you have a cluster algebra with initial cluster variables, and then when you mutate, remember by Laurent phenomenon, it will be a polynomial divided by some monomial. And there's a explicit description of the power of this monomial in terms of counting the tag arc. So let me just briefly discuss the denominator theorem in the last few minutes. So first, let's define the not the. So let's define what we want. So we have an initial seed. And any cluster variables can be written as a polynomial in the initial seed divided by the monomials in this initial seed. So this term here will be the denominator vector. And we want to describe this vector. So to give the description, we first make some definition. So the intersection number of two tagged arcs. So here we assume that they intersect transversely and say in the minimal number of points. So the intersection number of two tag arcs will be defined by this symbol. And this is expressed in terms of 4 numbers. So the first number is the real intersection. So it's the intersection of the undone version, ignoring the endpoint. So you just look at the untagged version and then count the number of intersections. B will be 0 unless alpha 0 is a loop based at A and with the undone version intersect at B1, Bm, then B is the number of contractible triangles formed by Bi plus 1 and A. So this may look a bit abstract. So let's say I have alpha, which is a loop based at A. And let's say I have some punctures outside. And then I have an arc beta, and let's say passes through like this. So it has several intersections with alpha, B1, B2, B3, B4, B5, B6, right? Then you count how many contractible triangles of the form Bi plus 1 and A. So for example, you have B1, B2, A. So this is a contractible triangle. B2, B3, A is not, it is just a line. And then you have B3, B4, A, and you also have B5, B6, A. So in this case, B will be -3. C is simple. It's just say -1 or 0 if the underversion actually coincides. And finally, D is the number of ends of beta sharing the endpoint with alpha, but tagged differently. So the standard situation. Here, then the number of endpoints sharing tagged differently will be 1, so D is 1 in this case. So just a warning. Usually, this intersection number is not symmetric. Just like the compatibility degree. It's really just like the compatibility degree we discussed earlier. So if we look at this example here, so let's say this is our beta, and this is our alpha. Then we can count and see that alpha beta will be 1, but beta alpha will be 2, using the previous definition. Now we can state our theorem. So recall that each cluster variable corresponds to a tag arc by our definition. So we'll denote the tag arc corresponding to your cluster variable by x alpha. Then the statement is that the denominator vector is exactly given by the intersection number of the corresponding tag arcs. Okay, so basically the proof really follows from verifying that it satisfies the recurrence relation coming from the mutation formula. So if this is your initial cluster, and remember, initial cluster means no tag arc. Then the denominator vector will be 0, not -1, if C is x. I mean, if C is the if C is the same as the variables that we are interested in, and 0 otherwise. And then we count that for a mutated variable, it satisfies the recurrence relation of the form. This is U. But this is exactly just like the mutation formula, but tropicalized, because you're only looking at the monomial power. Where the cluster we're interested in is the mutated one, where you replace Z by the new variable C prime. Yeah, so here, I mean, I should write this x is the x, the vector. So yeah, so this is really a vector. Where the xi are the initial variables. Right, so that is the description. The main idea basically is just you check that the cluster mutation formulas, you look at the monomial denominator, which is just the tropicalization. So it's given by this formula. And you check that the A plus B plus C plus D sum satisfy this recurrence relation. So it takes some calculation in the paper, but otherwise this is the main idea. Yeah, so maybe I should put an I here just to be clear. So Z will be initial cluster. I mean Xi will be the initial cluster and Z will also be initial cluster. Okay, finally, we also want to remark that there's another description of the coefficient of the polynomial. And this is given by counting perfect matching of some graph called the snake graphs. So let's say, what is a perfect matching? So it is a way to bipeptide your graph so that it consists of edges that is disjoint but covers all the vertex of your graph. So if you can have a description of such a polynomial in terms of counting something, then it really is saying that you have positive coefficients of your Laurent polynomial. And this is the way they prove the positivity conjecture by, so this is the work by Musiker Schiffler. And these graphs will be some combinatorial object constructed out of the surface associated to this classic algebra. All right, so this is overrun a bit. So thanks for your attention if you are still listening. In the next class, we will realize the cluster variables in terms of some coordinate system called the lambda coordinates on the type theory. And so this gives you a geometric meaning of all these numbers. And we can then also see that the autonomy relation, which is trivial in the Euclidean case, actually becomes the main mutation rule in the hyperbolic setting. Okay, thank you very much for your attention.